Hey everybody. So as you can see, we're gonna take a look at some inverse trig integrals, and similar to what we did with exponentials and logarithms in a previous video, we're just going to use what we know about derivatives to make rules for antiderivatives. Right? This makes sense. So let's just jump in and recall that in differential calculus, we derive that the derivative of sine inverse of x, let me just write this another way, so in case you're more familiar with seeing arc sine, those are the same thing, that we can, this derivative turns out to be 1 over the square root of 1 minus x squared. Okay, so that's or let's just write it one more way. Okay, so with this derivative in mind, we get the almost inverse rule that if we have this antiderivative, we know that this is an antiderivative of 1 over the square root of 1 minus x squared, and to make it more general, we put the plus c on the end, right? There's a family of functions that have this same derivative, 1 over 1 minus x squared. So this gives us a nice rule, and this is a great rule as is. We can actually push this a little further. We can generalize this just a bit. We can, let's take a similar antiderivative, where instead of 1 minus x squared, we've got a squared minus x squared. And let's just take a to be positive. We're squaring it anyways. If there's a negative in there for some reason with the squared, you can use absolute value for this result. I'm going to do it with a being positive. So let's see if we can come up with the antiderivative here using this rule. So we already have one rule about, whoops, as straight as I wanted. Sometimes it acts a little funny. Let's see if we can use this rule above to get a more general antiderivative for this form anytime we have a constant minus x squared. So let's first do a little bit of algebra. I'm going to do this off to the side. If I take a squared minus x squared, I can factor out a squared, and I get 1 minus x squared over a squared. Using the rules of exponents, or in this case rendered as radicals, I can take that a squared factor in its own radical. I'm also going to rewrite x squared over a squared as x over a, the whole thing squared. And then if I take the square root of a number being squared, I get that number. Of course, this relies on the fact that a is positive. If I hadn't insisted on a being positive, this ends up being the absolute value of a, but I took this route. Let's take. Okay, so I'm going to replace what we have in our integral, the denominator here, with what I've just worked out off to the side. So this becomes a 1 minus x over a squared dx. Okay. And then I can take the 1 over a out front. All right, so now if we look at the integral that we have here, right, we've got this constant out front. We're not going to ignore it, but I don't need to think critically about it right now. If I look just at the integral part, I see something very similar to what we have in this rule up above. So let's see if we can make a substitution to get it more exactly like the rule up above. So notice I have x over a instead of just having my variable squared. So I'm going to try to use the substitution u equals x over a, which will give me that du dx is equal to 1 over a, or du is equal to 1 over a. Actually, I'm going to put the a over here. It doesn't matter. There's different ways to do this. This is the way I like to for some reason. So I've got a times du is equal to dx after a little bit of manipulation there. Okay. So let's now put our substitution as in. I've still got 1 over a. I've got 1 over the square root of 1 minus that x over a becomes u squared. And then I pick up a factor of a and then a du. Now we've got a factor of a and a factor of 1 over a. I can bring this a out front and those two factors will cancel. And what I'm left with is this, which we now know to be, thanks to the rule up above, sine inverse of u and plus c. And then putting our substitution back in, I get x over a plus c. Okay, so that works out pretty nicely. This is a case where we could have been right for the wrong reasons if we had just applied the rule naively at this point where we have x over a and just treated it like that. But you don't always know how it's going to work out. And so we get this nice rule, okay? So let's write that as our most general rule. So let's see. The rule we've just discovered is 1 over square root of a squared minus x squared dx is equal to the inverse sine, or the arc sine of x over a plus c. You'll sometimes see this written with absolute value bars around the a. I chose to make a positive. We can do it with absolute value. Just changes a little bit way of how we manipulate the equations up above. In a similar way, we can get rules for some of our other inverse trig functions. So for instance, if we see something of this form, we end up with 1 over a tangent inverse of x over a plus c. And then one more, we'll have 1 over x times the square root of x squared minus a squared dx. And this one turns out to be 1 over the absolute value of a secant inverse of x over absolute value of a plus c. Okay, so you can work those ones out in a similar way as what we did in the beginning of this video to derive those rules. They just all work by starting with the derivative we know and then generalizing with some probably usually substitution. Okay, so let's just do a couple of quick examples of using these rules. So let's start with a pretty straightforward one. So let's say I have, let's do a definite integral. Let's say I have an integral from 1 over the square root of 3 to the square root of 3. Of 1 over 1 plus x squared dx. Well, looking at our chart, our set of rules, I see this is the second form where a is equal to 1, so I can just follow this pattern. If a is equal to 1, this is 1 over 1, so I don't need to write that, and I get the inverse tangent of x over 1. So I'll have this, and this is going to be evaluated from 1 over the cube root of the square root of 3 to the square root of 3. So this is tangent inverse square root of 3 minus tangent inverse 1 over the square root of 3. If you remember your unit circle, this one is pi over 3 minus pi over 6, which is going to just be pi over 6. Okay, so just a simple application of that rule. Let's do one more example. Let's take the integral e to the t over 1 minus e to the 2t dt. Okay, so now this one doesn't look exactly like one of these, but we can use a little bit of algebra here. Let's use some rules of exponents to rewrite this thing. So I want to write e to the t over the square root of 1 minus e to the t squared dt, right? So that's just how exponents work. Well, now notice that this thing in the denominator looks very much like the thing we have for inverse sine, the function in our rule, with a little bit of substitution. So let's do that now. I can substitute, let's take u is equal to e to the t. Du will be e to the t dt. And so putting these substitutions in, the e to the t dt in this e to the t in the numerator dt gives us du. And I have a 1 up here, and then I have 1 minus u squared. Now this fits right into our rule with a equal to 1. And so I get sine inverse of u plus c, and then sine inverse, putting back in the substitution, e to the t plus c. Okay, all right, that's it for these. Obviously, there's a lot more you can do, but they're just pretty standard rules that we can derive from our derivatives. I'll also encourage you, take the derivatives of what we get at the end to check your work. I'm going to leave that up to you to see if these antiderivatives I found are indeed correct. Okay, thanks everybody. That is it for this one. I will see you next time.